Hello, everyone, and welcome. So today we're going to tackle a very important topic from our first unit, electric charges and fields, and that topic is electric field lines. Now, this is a super interesting concept, you know? It helps us to actually see forces that are otherwise completely invisible. And I can promise you, by the end of this session, this whole idea will be so clear that you'll feel absolutely confident about it in your exams. So here's our game plan for today. First, we're going to understand why we even need this concept in the first place. Then we'll look at the official NCERT definition, the one that gets you full marks. After that, we'll cover the simple rules of field lines, talk about some common mistakes that can cost you marks, and finally, we'll wrap it all up with a quick summary. All right, let's begin. All right, so first up, visualizing invisible forces. What are we even trying to do here? Well, we're basically trying to find a way to see forces that we can't, actually see with our eyes. I want you to really think about this for a second. How does one charge feel the force of another charge from a distance without any contact at all? You've seen this with magnets, right? You bring them close and you can feel that push or pull even before they touch. It's the exact same thing with electric charges. So the big question is, how does this happen? What's going on in that empty space between them that's carrying this force? Well, the answer to that little mystery is a very powerful idea in physics, the idea of a field. You see, every single charge creates this invisible zone of influence all around itself. We call this the electric field. So when you bring another charge into this zone, it's the field at that very spot that pushes or pulls on it, creating the force we observe. Now, this is where it gets really clever. To help us actually understand this invisible field, the great scientist Michael Faraday, he came up with a brilliant idea. He thought, what if we could draw a map of this field? He wanted to create a simple, visual way to picture it, without all the complicated math. And that's what he did. He invented what he called lines of force, which today we call electric field lines. And this idea becomes super clear when you look at a diagram like this one. Just take a look at this single positive charge. See those lines radiating outwards? Those are the electric field lines. Think of it just like a map. And this map tells us two very important things: the direction of the electric force and how strong that force is. It's a really simple but powerful way to see something that's totally invisible. Okay, so now that we have the general feel for what these lines are, let's get into the official stuff. This is the NCERT definition, the one you absolutely need to know for your exams to get those full marks. Let's read it together carefully. An electric field line is, in general, a curve drawn in such a way that the tangent to it at each point is in the direction of the net field at that point. Okay, so that sounds a little bit technical, doesn't it? Let's break it down. What does that actually mean in simple words? It's actually much simpler than it sounds. Imagine you have a field line. It could be a straight line or a curved one. Now, if you want to know the exact direction of the electric field at any point on that line, all you have to do is draw a tangent to the curve at that specific point. The direction that the tangent points, well, that's the direction of the electric field right there. That's it. That's the key idea from the definition. All right, now these field lines aren't just drawn any which way. They follow a very specific set of simple and logical rules. You can call them their properties. And you really must know these by heart. There are four main rules we're going to cover. Okay, rule number 1. Field lines always start from a positive charge and they end at a negative charge. Simple enough. Rule number 2. In a region with no charges, they are continuous curves. They don't just stop and start again. They have no breaks. Rule 3, and this one is super important. 2 field lines can never cross each other. Never, ever. And finally, rule 4. These electrostatic field lines do not form closed loops. Now let's see what all this looks like in pictures. So take a look at these examples. For a single positive charge on the left, you can see the lines start on the charge and radiate outwards, heading off towards infinity. And for the single negative charge on the right, the lines seem to come from infinity and they terminate or end right on the charge. See? This is a perfect illustration of our first rule. Now this is where things get really cool. Look at how these simple rules create these amazing patterns. On the left, you've got 2 positive charges. Notice how the field lines seem to push away from each other? They bend outwards, visually showing us the repulsion between them. But on the right, with a positive and a negative charge, a dipole, you can see the lines starting from the positive charge and then gracefully curving around to end on the negative charge. This is a perfect picture of attraction. And hey, remember I said the map also tells us about strength? Well, here's how. It's all about how close the lines are to each other. In regions where the field lines are packed closely together, like near the charge itself, the electric field is very strong. And in regions where they are spread far apart, the field is much weaker. So just remember this: closer lines equal a stronger field. As simple as that. Okay, now for a classic conceptual question. This is a favorite in exams, so pay close attention. Why can two field lines never, ever cross each other? Just think about it for a moment. Go back to the definition we learned about the tangent. What would it mean if they actually did cross at some point? And here's the reason why. If two field lines were to cross, then at that single point of intersection, you could draw two different tangents, right? One for each line. And since the tangent gives the direction of the electric field, this would mean that the electric field at that one point is pointing in two different directions at the same time. And that is just physically impossible. A force or a field at a single point can only have one unique direction. All right, let's move on to a very important section. Here, we're going to bust some common myths and misunderstandings that can easily cost you marks in your exam. Think of these as the silent killers of marks. Okay, first big mistake. A lot of students think that a field line represents the actual path that a test charge will follow. That is incorrect. The tangent to the line only shows you the direction of the force at that one instant. A charge will only move along the field line if the line is perfectly straight. The second wrong idea is thinking that these lines are real physical things existing in space. They are not. Remember, they are just an imaginary but very powerful visual tool that we use to represent the real field. Okay, so let's start to wrap this up. We'll do a quick summary, and then I want to show you why getting this topic right is so crucial for what we're going to study next. You see, mastering the concept of electric field lines is absolutely essential for understanding our next big topics, electric flux and Gauss's law. In fact, the idea of electric flux is basically about counting how many field lines are passing through a certain area. So, if you've understood this visual map properly, then understanding flux is going to be so much easier for you. It's the foundation. So, to quickly recap the key takeaways. What are electric field lines? They're a visual map of the electric field. Where do they start and end? They start at a positive charge and end at a negative one. How do you find the field's direction? The tangent to the line at any point gives you the direction of the field E. How do you know the strength? The density of the lines shows you the strength. And what's the golden rule? They never ever cross each other. And before we finish, I want to leave you with one final thought to ponder. Isn't it amazing that something completely imaginary, just a picture we draw with lines, can so perfectly describe the behavior of a very real and powerful force of nature? That, right there, is the beauty of physics. Think about that. I'll see you in the next class.